Hello and good morning everyone. Today inshallah we will enter a new chapter. Today lecture, it's the first part in linear transformation, which is a very important part. In the previous sessions we already tackled chapter 4. We went through the vector spaces and all about vector spaces, from the spans, from the bases, from the addition, intersection, union, and we also learned in vector spaces how we do the matrices or use the matrices within the details of vector spaces. Now, today's lecture, we will start a new topic which is really very important in linear algebra in general, which is the linear transformations. And as you can see, this is chapter number 5. Still we have 6, 7, and 8 to go chapter. This chapter is important and it contains a lot of information, so I want you to go with me step by step. First, linear transformation fundamental concepts, as I told you, in linear algebra, connecting vector spaces and preserving their structure. What's the meaning of preserving their structure? It preserves the addition and the homogeneity properties. So, a linear transformation is a function. What's a linear transformation in general? It's a function that moves stuff or map stuff from vector space V into vector space W. So I will have a function that will have sources or input from V, and the output will be the image in W. Both of them are both two sub-vector spaces or two vector spaces. V and W over the same field satisfying two key properties, which are, if you remember, the properties of the vector space and sub-vector space. The first of them is the additivity, this division of vector addition, which means this function will preserve the addition, the addition closure probability in those vector spaces. So a function with u plus v will result into f of u plus f of v. They will be the same for both u of v belongs to the input, and the homogeneity, which means the preservation of the scalar multiplication, which means the function or the linear transform of c and v, it will equal to c times f of v, where c belongs to the real set or the k set in a much larger scale, which represents either real numbers or complex numbers. Now, the application of linear transformations in every field, actually in STM, science, technology, engineering, and mathematics. So mainly for computer graphics, rotation, scaling, translations, and projections. For data sciences, principal component involved linear transformations. In physics, description of rotation, reflection of quantum mechanics. In engineering, solving system of linear equations and signal transformations. So a wide range of applications, as you saw in science, technology, and engineering and mathematics, and also a key theory in understanding the operations down the road, going through a variety of various fields in engineering. The definition and examples, if we consider in this chapter that E dash and E double dash are vector space over K, which means real set or complex set. Okay, overview of R. Remember the probabilities of vector space, which is the addition and the multiplication of linear transform. Multiplication of the scalar. Jana, the linear transformation means a function that will move objects from a vector space E into E dash. In order to imagine exactly what I'm saying, let's start with a hint clue about this. I can say, for example, that f is the function for R3 into R2, for example, which means a function that will have input from R3 and the result or the final result will be output in R2. For example, okay, Ms. Jana, if R3 is X, Y, and Z, after mapping the function of x, y, and z will result in, let's say, 2x plus y and z minus 1. So actually, I will take elements of x, y, and z, and I will map them into the form of 2x plus y and z minus y. So now I'm moving from R3 into R2. That's the function which is the meaning of a linear transform or a transform from R3 into R2. Today, inshallah, we will see plenty of examples. Moving stuff from R3 into matrices, or from matrices into R3, or from polynomials into matrices, and vice versa. It's really very interesting topic. Okay, so once more, as I told you, that's an example of a transform. So mainly, to be a linear transform, okay, remember the word linear, you will have to preserve the two main key operations in vector spaces, which is the addition, closure, and the multiplication by scalar closure. This is why even the order you have taken vectors and some vector spaces, then we will talk about the linear transformation. Okay, meaning we are having moving representing elements of E into corresponding elements of E dash, exactly as we saw. And those are the conditions for the linearity. Okay, I can move stuff, plenty of stuff. For example, I can reduce some vector or increase the size of vector. So I can move, I can do a dilation, okay? Consider the function that moves E into E, but with this function, with this transform. It's like scaling, multiplying W in a scalar value, and you will see the image either increasing or decreasing, okay? And it's called a dilation. So if is a linear transformation, that's we call a dilation of a ratio of B. This is a linear transformation because it satisfies the properties of addition and multiplication by scalar. If beta is equal to 0, so I'm mapping the elements of W into the origin, and in this case, we call it the null transformation. So I have the dilation transformation, which is scaling. If we are moving stuff from the input to be mapped into the origin, then we will call it a null transformation, okay? Or the null transform. Mapping element of E into the 0 of E. Because for this one, for the dilation, if you have F, U1 and U2, for the null linear transformation, I can prove it's already linear, its linearity, because simply if I have F of any vector will be mapped into the origin. If I have vector 1, U1 and vector U2, and they added them together, the image will be in the 0. If you get each one of them separately, the result also will be 0. If you multiply C times U, it will be mapped into the origin. And also, multiplying C and the F of U, that will be the origin, the result will be the same, which means it's a linear transformation. So, either both of them. Also, we have a very famous transform also, which is the ideal transformation, which means transforming U into U, or moving the stuff exactly the same image. So I'm making a translation or transformation x, y, and z into x, y, and z. And it's called, in this case, mapping into elements of itself, and we call it the IDE of E, and it is such that E is mapped into E. We call it the identity transformation. But for the time being, we already know what's a linear transformation. It's a function that moves stuff from a vector space into another vector space. How the function is working, this is how the transformation is going to go. We have conditions for the linear transform. The linear transform must preserve addition and scalar multiplication. I will give you examples shortly. Okay, we have, till the time being, we have 3 types of linearity or linear transform, which is the dilation, which means I'm going to multiply certain vector by a quantity. I have the null transform, which means you will map all the elements in the N subvector space into the origin of E. I have the ID identity transform, which transforms E into E. ودايما احنا بنشوفه for every U belongs to E, the IDA of U is equal to U. And of course, it's a linear transform also. Simply can be found as adding the function of U1 and U2 will be mapped into U1 and U2, and if you multiply by a constant, you will have the same result, so it's a linear transformation. طيب, for a transform which is moving real into real, so I'm moving real numbers and it will be mapped into real numbers. How they are going to be mapped? It will be mapped by this function. خلي بالك ان linear transformation concept another to apply it on functions, other to apply it in plenty of objects. هنا في الوضع اللي انت شايفه قدامك انا بابلاي linear transformation ده اوكي على straight line. يبقى انا بعمل linear transform from real numbers into real numbers. طب ازاي هيبانوا معايا فريد؟ هيبانوا عن طريق ان f of x يساوي n x plus b. يا ترى الاستفسار بتاعي ده linear transform؟ This is not going to be a linear transform except b is equal to 0. لو b بيساوي 0 ده هيبقى dilation وهيبقى linear transform. لكن لو b دي بتساوي any number it's not going to be a linear transform. طيب it's really very easy to prove. ازاي؟ how to prove it؟ خلي بالك ازاي اقدر prove it؟ Simply I will use x1 and x2. هاخد two values from x1 and x2. So after mapping it's going to be m x1 plus b and m x2 plus b. That's the two values, m x1 plus b, m x2 plus b. If you add them together, you are not going to have mx plus b. You will have m of x1 plus x2 plus 2b, which is a violation for the addition property. Also, if you multiply by a constant, معايا مستر زياد, it seems like انك بتحاول تتابعني يعني. لو انا عندي f وعندي c في x1, it's gonna be c x1 m x1 times b. Exactly like if I have f of x1, which is mx plus b, if you multiply it by c, you will have cm x1, which is exactly the same, the first term, but the second term is going to be cb. So it's also a violation for the multiplication by scalar. So for a linear transform from R into R using mx plus b as a function of the transform, it's not going to be a linear transform. Okay. Look to this application also. Ms. Jana, please leave yourself. He is asking you the function b such that R sub n of x, it's a symbol for a polynomial. Now I will consider my linear transform to do a derivative. So I'm considering another way to explain how the derivative goes. Okay? Is it a linear? Can we consider it as a linear transformation or not? So if I have, for example, an an x to the power of n, an minus 1 x to the power of n minus 1, and so on, which is a polynomial of degree n. If you find the derivative, the power will go down and you subtract 1 from the power. So it's going to be an xn times x to the power of n minus 1, and so on, with all the values. If this transform can be considered a linear transform, in order to be sure about the linearity, you will have to prove two relations. Closure of the addition and the multiplication by scalar. So all I have to do is once more consider that for a polynomial of x1, for a polynomial of x2, if you add them together, you will have the derivative of x1 plus the derivative of x2, which proves exactly the two properties, the addition property and the multiplication by scalar. لو انت عندك function جبت لها الديريفاتيف بتاعها وفانكشن تاني بولينوميال جبت لها الديريفاتيف from the same degree وعملت لهم addition, it will prove the addition property. لو عندي function polynomial of second degree, third degree multiplied by a constant وجبت الديريفاتيف exactly like انك تعمل ديريفاتيف تضربها في constant, صح؟ الاثنين زي بعض, which means it is a linear transform. And the definition of linear transformation, the conditions 1 and 2, two conditions دول اقدر اكتبهم بالشكل ده والشكل ده. طيب تاني once more, linear transform عشان يبقى linear محتاج كام condition؟ 2 conditions. The first of them is the addition. This some vector spaces or vector spaces. So for u and v, f of u and v بالظبط بتساوي f of u plus f of v. صح؟ والmultiplication by scalar, if I have f times cu, it's exactly like c times f of u. Okay? طيب, instead of writing these 2 conditions, I can write this condition only. If you look to this condition, it's a combination between the multiplication by scalar and the addition. Okay? So it's equivalent to both of them. Or even to write it on this form. Multiplying just one vector in some constant, and the result will be alpha f of u plus f of v. It's also replacement for these 2 conditions. If I can do the conditions separate, the addition and the multiplication, and I can combine them. If one of these conditions satisfied, either the first 2 or one of the third and fourth, so it's gonna be a linear transform. Once more, Ms. Seda, in order to follow up with us very easily. A linear transform is one. It's simply a function that moves the stuff from subvector space into another subvector space under certain condition. This condition may move or map from R3 into R2, from R2 into R3, or from R3 into R3 for simplicity. يعني مثلا انا ممكن يبقى عندي linear transform برضه يا فريد لو انا عندي f لف دي such that بتماب stuff from R3 into R3. طيب ازاي هيحصل المابنج؟ الفانكشن دي بتشتغل ازاي؟ يبقى الفانكشن دي الانبوت R3 الاوتبوت هيبقى برضه بمين؟ R3. For example, I can say ان f for an I3 x y and z will be mapped in. يبقى الفانكشن دي لما توصل x y z هتبقى مابد في ايه؟ بسيطه قوي اهي y z and x يبقى mapping my R3 into R3. بس الكوردينيشن اختلف عشان لو عندي فاكتور 1 1 1 2 3 completely different than 3 to 1. Am I right? Completely different than 2 3 1 for example. Or I can do from R3 into R2. Simple. I can choose, for example, like this. So it's a mapping from x, y, and z into 2 components, which is from R3 into R2. Am I right? Also, I can map from R3, for example, into a polynomial of second degree into B2. How it's going to be mapped? This is x, y, and z. So my equation will be x times x capital square plus y times y capital plus the value of z. So simply the coordinates here will be mapped into a second polynomial. Are you with me? I can do another transform mapping R3, for example, into an M2 by 2. I'm taking a function that will move, function such that it moves the stuff from the 3 dimension into a matrix 2 by 2. How it's going to be done? The function in x, y, and z, for example, will equal to x for the first element, y plus z minus y minus z. So I'm moving the stuff from R3 into matrices, or from R3, are you with me, Jana, into a polynomial, or vice versa, or even moving from R3 into R3 with a special function, or moving from R3 into 0. I'm moving f such that from R3 into R3, where my function in x, y, and z will appear in 0, 0, and 0. And that's the null transform. Or it can be an ID transform from f of x, y, and z into x, y, and z. So I'm moving just the plan into itself. Are you with me? Or making dilation either by scaling, minimizing, or maximizing. I'm moving x, y, and z into 2x, 2y, 2z. That's the linear transform. Many. So the idea about the linear transform, it's a function. So it can work with functions, it can work with derivatives, it can work with plenty of applications. Even it help you out to move just a measure, to move from R3 into matrices or from matrices into R3, and vice versa. It's really very interesting. Okay? So the concept, in order to be a linear transform, it has to preserve the main two case or the main two conditions of additivity and homogeneity. The additivity, it means it preserves the addition. Homogeneity, it preserves the multiplication by star. معلش خلينا ناخد دي براحه عشان الحركه دي يدفع فيها فلوس. Okay, linear transformations. I will talk about operations with functions. So, okay, now if I have f such that خلاص انت بدات تتخيل يعني ايه linear transform. From E into E dash, whatever بقى E ده R3, E dash R2, whatever بقى, ماشي? Okay, and G from E into E dash, be some arbitrary functions. We call some functions of some function of the functions of F and G, of F and G, and we symbolize it by F plus G to F plus G such that E into E dash. You know, I have two functions completely separate. Two functions, so they are moving stuff from subvector space E into another subvector space E dash. I can add them together. Are you with me? Also, we have F and G are arbitrary functions. Also, the multiplication by scalar. So if I have F which scale E into E dash, also by multiplying alpha F, it's going to also preserve the probability of the multiplication by scalar or the homogeneity. Okay, perfect. So linear transformation is preserved through these two operations, multiplication by scalar and so on. Also, I can do multiple linear transformations. So I can use F, for example, to move stuff from the vector space A into vector space B. Then I will change and use another function that will take this output into another output. So I'm moving from A into B and then from B into C using a certain steps in linear transformations. This is what's written here. Let A, B, and C sets subvector spaces or vector spaces. And F is such that it will take input from A, map it into B. G will take the output here and map it in C. Okay? طبعا لازم يبقى في كونديشن توافق ال R2 وال R3 يعني الدايمنشنز بتاعت السبفيكتور سبيسز دي. يعني for example بص if I have F moving the stuff from R3 into R2 for example, so G must make elements or must take transform from R2 into whatever you want to do. Am I right? Because the output here is going to be the input in G, and that's a very important remark you have to keep in mind. So if this transform is happened, we call it a composite transform يا فريد. واقدر اسويه كده such that G composite F, which means G is a composite of F of A. So F will start from A into B. Then G will take B and move it into C. Now I can move G composite F as A from C as a linear transform. So I can also use compositions. So I can use addition, I can use composition in linear transformations. Of course, the composition of two linear transformations is a linear transform. Let A be a set such that from A into E be a function and the K belongs to the set of natural numbers. We call it power of exponent K of F, and we symbolize it F to the power of K such that from A into A. خلي بالك ان F of K is between two things. K is taking all the scalar values, either complex or real numbers. So if K is equal to 0, you will end up having from A into A, which means the ID transform. The ID transform فاتن, it moves A into A. يعني بيحرك elements من نفسها بعض, يعني vector into itself. طيب لو هو f of k means f of k of minus 1 if k belongs to n. ده الايدنتيتي ترانسفورم طبعا number 1. Exercises on linear transformations. This is really very interesting about. In order to see if it is a linear transform or if it is not a linear transform. Okay, determine whether of the following functions, which if you remark a function that maps elements from R3 into R2. يبقى function دي او linear transform هيعمل ايه؟ هياخد 3 ابعاد يرميه ببعدين. تمام كده؟ 3 dimension into 2 dimension. How it's gonna be done? The first of them, it will take x, y, and z. The image يعني ده will be y and 0 only. يبقى كل element انت تستخدمه x, y, z as an input، الايمج هيطلع فيها مين بس؟ y و 0 صح؟ It is like getting a projection of x, y, and z on the y-axis. I'm sorry, on the x-axis. On the x-axis. Okay? So, in order to see if this is a linear transformation or not, how many probabilities I should check? Just only two. The addition and the multiplication by sum. Okay, I will do it with you step by step. For the derivative, I will take u and v belongs to the input function. Right? It will be mapped into the output. And then I will take the left hand side, then the right hand side. Exactly the same manner for the second condition. So if I started to determine whether each of them is a linear transformation, I will check f of x, y, and z is equal to yz. So I will take 2 points. Let's say x1, y1, z1. It will be mapped in y1 and 0. Then x2, y2, z2. It will be mapped in y2 and 0. Add them together and see if the probability hold or not. So once more, here we go. That's x1, y1, z1. That's the second point, x2, y2, z2. So I'm taking the right hand side, this hand side. U plus v, that's u and plus that's v. Okay? So once you add u and v, it will be added together. x1 and x2, then y1 and y2 for the second component, z2 and z1 and z2. صح مش جاي؟ طيب هيماب ازاي؟ بيظهر السكند كومبوننت تو زيرو. مين السكند كومبوننت هنا؟ y1 and y2. So that's the image. يبقى انا كده اتكلمت على الليفت هاند سايد. اروح امسك الرايت هاند سايد. معايا يا فريق؟ الرايت هاند سايد لما ابلايت على x1 y1 z1 هيدي لك y1 0. لما ابلايت على x2 y2 z2 هيدي لك y2 0. Once you add them together, you will have the same result. اهو. On the other hand, f of x1, y1, z1, f of x2, y2, y1 0, y2 0, the result is exactly the same. So the addition probability holds. نفس الاسلوب بالظبط. Let's say that. I will do it with the multiplication by scalar. So I will start first having x1, y1, z1 times c, and I will see the image. Then I will bring f of x1, y1, z1. Then I will multiply by c, see if they equal to each other or not. Once more. This is the first probability holds. I'm going to the second probability. I will multiply c in x, y, and z. So the image will be c, y, and 0. Then take the c out. Get the function on x, y, and z, which is going to be y and 0. Then multiply by c. As you can see, the two results are equal to each other. So the multiplication by scalar hold. So this is a linear transformation. Both of them exist. This is the addition, and that's the multiplication by scalar Bijana. So it means you have a linear transformation. Okay, let's try it once more on x minus 1 and 1. مين يعملها معايا؟ فريق اشتغل معايا كده. عايز اتشيك الاديفيتي اعمله ازاي؟ سهل قوي. اروح رايح جاي a function of الفيرست فيكتور x1 y1 z1 plus second vector x2 y2 z2. طبعا لما بجمع دول على بعض معايا فريق هيديني a function فيها الفيرست كومبوننت x1 plus x2 simple logic y1 plus y2 z1 plus z2. This is the input. ده الانبوت اللي انا بدخله. الاوتبوت لازم يبقى كده. يعني ده معناه ان الاوتبوت بتاع this function is gonna be the first component minus 1. So it's a x1 plus x2 minus 1 and y, which is y1 plus y2. That's the image. using the linear transform on the addition. I will do it separately. So I will try to get f of x1, y1, z1 separate, which is going to be the first component minus 1 and the second component. I will do exactly the same, but with x2, y2, z2 yazid, which is going to lead to x2 minus 1 and y2. Then I will add them together. So now I will get f of x1, y1, z1 plus f of x2, y2, z2, and it's going to lead to add them together. Once you add these two guys together, you will have x1 plus x2 minus 2, then y1 plus y2. This is the final result. Is this value equal to that value? No. صح. يبقى الاديفيتي property doesn't hold. So it's not a linear transformation. Also, if you want to check the multiplication by a scalar on the same debate, same way like, I will start for the second check. If you want to do the second check, of course, it's خلاص, not a linear transformation. But if you want to go for the second check, it's exactly the same. I will try to get f of c of x1, c of y1, c of z1. And the result is really very simple of this transform. It will get the first component, which is cx1 minus 1, and the second component, which is y1. Then I will try to do the other side. The other side, get the transform first of x1, y1, z1, which is gonna be the first component and this minus 1, sorry, okay, and the second component. Then multiply by a constant. Once you multiply by a constant, you will be ended up with c of x1 minus c and the c of y1. Is this result equal to that result? مش انت بتضرب السي في x1 y1 z1؟ ليه في اول واحده؟ ما هي اللي فوقيها ازاي مش سي y1؟ لا لسبب بسيط، لان انت لما بتشتغل الفانكشن بتاعت الترانسفورم بتاخد الفيرست كومبوننت تشيل منه واحد وتحط جنبها السكند كومبوننت. ده اللي حصل عندي هنا. خدت الفيرست كومبوننت اللي هي سي اكس ماينس 1، صح يا فريق؟ شالت منه واحد وخدت سوري انا اسف، وخدت السكند كومبوننت اللي هي سي واي 1. بس طبعا التو كومبوننتس مالهم نوت ايكوال تو ايتش اذر. هنا ده سي اكس 1 ماينس 1، هنا ده سي اكس 1 ماينس سي. You read me? So even the multiplication by the scalar, it doesn't hold. Are you with me? يبقى اذا it's not a linear transformation. شباب متابعيني؟ المفروض ده سهل. اوكي مجرد وخطأ. السهوله فيه انه ستيبس سيستماتيك. انت هتمسك يا دوبك انا بحاول to prove the both identities, the multiplication by scalar and the additivity property. اهو ادي additivity وادي homogeneity. Step by step, left hand side will leave you with the first component minus 1 and second component. لو انا bring everyone separately and added them together, this is going to be a negative of 1, this is going to be a negative of 2, so it doesn't hold. يبقى ما هواش على طول مش همشي في السكند ستيب، يعمل بدايه باص يبقى ده يبقى نوت linear transform. اوكي طيب لو انا عندي ده x y and z will be mapped into x y and 0. This is a linear transform. قدامي ده linear transform. برضه بنفس الاسلوب لو انا عملت الادافيتي ولو عملت الهوموجينيتي. If you do the additivity, I will have x1, y1, z1, x2, y2, z2. That's the sum of them. So the appearance will be x1 plus x2 times y1 plus y2 and 0. If you get each one separate, you will find x1, y1, x2, y2, and you will end up having this result. If these two ends equal to each other, no. It's not equal to each other. معايا كاتب؟ طيب يبقى إذا على طول it's not linear transform. even though if you want to go for multiplying by a constant number, you will end up having c squared x or y, and this is cx, the other side is going to be c of x and y, and also it's not going to hold, so it's not a linear transform. See also this example, if I have x1 and z, and I have x and absolutes of z, which of course is not going to be a linear transform, because simply the لا مش زي
ازاي في زي في التو دايمنشن؟
زد في التو ده هو اسمها تشويس. مش في زد في التو دايمنشن، هم هاو ماني كومبوننت؟ 3 كومبوننت، ده الانبوت. الثلاث ارقام اللي هم محطوطين في الانبوت دول هيظهروا كاوتبوت. الاوتبوت بتاعهم هياخد ايه؟ هياخد الفيرست كومبوننت هنا تو بي ذا فيرست. طب السكند كومبوننت هنا هياخد الفاليو دي، مش دعوه بقى اسمها زد بت اي حاجه، بس هياخد الفاليو دي مالها كمان؟ ابسوليوت. يبقى انت بدل ار3 بدات تعمل له مابنج انتو مين؟ انتو ار2. طيب يا ترى ده لينير ترانسفورم؟ بالتاكيد مش هينفع. ايه اللي خلينا اقوله بالتاكيد مش هينفع؟ لان according to the absolute properties, the absolute of x plus z is not equal to the absolute of x plus the absolute of z. صح؟ صح؟ انا عندي two numbers بجيب their sum first وبعدين اخد منه absolute. مش زي ما اجيب الابسولوت for the first value والابسولوت for the sum. partially correct، لكن في بوزيتيف ونيجاتيف مش هيبقى صح. اوكي؟ طبعا الاديتيف probability اهو، that's for the first as I told you, and that's for the second. It's gonna be a failure, it's not gonna hold, simply because z1 plus z2 absolute doesn't equal to the absolute of z1 plus the absolute of z2. So this is why it's not a linear transform. طيب تعال بص على linear transform ده اللي انا كنت بقولهم لك من الاول. تحفه. بص على linear transform ده بيعمل ايه؟ بينقل، خلي بالك، بينقل من R3 into 2 by 2. بس قبل ما اكمل حد يقدر يقول لي مين هي البيزس بتاعت R3 والدايمنشن بتاعها؟ What's the basis of this guy and its dimension؟ ده سؤال تعرف تجاوب؟ ها؟ نقول مين؟ فاتن. قولي لي، نظرة في عينيك خطيرة. قولي لي بقى البيزس، ها؟ لا اديها تشانس، اديها فرصتها.
قول يا زلمه.